All right, so we already have discussed the different methods in solving the first order differential equations. Now we move on to the applications of these first order differential equations. Um, so far we're only discussing basically the theoretical side of differential equations for first order. Now, where do we actually apply this? So first, one of which is the Newton's law of cooling. So the Newton's law of cooling states that the rate at which a body cools is proportional to the difference between the temperature of the body and that of the medium. All right, so let's write that in an equation, or let's put that definition to an equation. All right, so it says here that the rate at which the body cools. So when we say rate, okay, so that is with respect to time, right? So that is basically what? The change in temperature over the change in time. So basically that's the rate, right? That is in terms of degrees Celsius or Kelvin or Fahrenheit per time or per second or per minute, right? And it also says that it is proportional to what? It is proportional to the temperature of the body, or the difference between the temperature of the body and the temperature of the medium. All right? So basically, the Newton's law of cooling is basically this equation. So it says here proportional. So it must have a constant. So this is now your rate equation. All right. So how do we apply differential equations here? So basically, this equation is a differential equation, right? Okay. So let's define first. So T is actually what? T is basically the temperature of the body. At time T. Okay, so T is time. K is the proportionality constant. And Tm is the temperature of the medium. So when we say temperature of the medium, when we say temperature of the medium, it is the temperature of the surrounding or the environment. So this is where an object is subjected to. All right, so how do we use, or how do we find the general solution to this differential equation? Okay, so as you can see, this equation, let me rewrite that. This equation is a differential equations. Now by variable separable, so let's separate dt, or change in temperature and change in time. So we have dt over T minus Tm is equal to k dt. So what we do after is that we integrate. So this is by variable separable. So that what happens? So here, as you can see, Tm and K are treated as constants. Alright, so that's basically just like x minus 1. Alright? Okay, so when we derive that, or we integrate that, sorry, if we integrate that, it becomes what? ln T minus Tm is equal to, so the integral of a constant is basically the variable to the first, or to the first power. So that is kt, and let's not forget the constant. Alright? So let's raise everything to the from the e. Okay, so we have e to the power of ln t minus tm is equal to e k t, or times c. So this will be cancelled out. So we have t minus tm. So this is basically what? ekt times e to the c. But this is still basically c. And so we have t minus tm c e to the kt. This is the general solution to the Newton's law of cooling. Alright, so let's put that into an example. So we have a sample problem here. It states that a thermometer reading 10 degrees Celsius is brought in a room whose temperature is 18 degrees Celsius. 1 minute later, the thermometer reading is 14 degrees Celsius. So how long does it take until the reading becomes 16 degrees Celsius? All right. So we've already derived the formula. So let's write the formula, or the general solution to that. So we have the T is equal to, oh wait, that's T minus Tm is equal to CEK to the KT, or that's basically T is equal to Tm plus CE to the KT. Now we have two variables, so we have two variables here that are not given. All right, so let's first have the first, or the initial conditions. So at time 0, so that is basically the initial condition. What is the temperature of the thermometer? So it reads 10 degrees Celsius. And the temperature of the environment, or the medium, is basically what? 18 degrees Celsius. All right. So let's put that into the equation. So let's substitute the values. Okay, so we have T, which is 10, is equal to, what is Tm? We have 18 plus, so C is not given, E to the K is not given as well, and T, what is T? So that is basically at time 0. All right. Okay, so this right here is actually 1. Okay? E to the 0th is, or anything raised to the power of 0 is 1. Alright? So, what do we do next? So, let's just simplify. 18 plus C. So, basically, C is C is 10 minus 18. So that is basically negative 8. So we already have our C. Okay. Next condition. So at time 1 minute, what is the temperature now of the thermometer? So it read 14 degrees Celsius. And the temperature of the surroundings, given that the surrounding is very big and it does not change to the individual objects inside that surrounding, so that is still basically 18 degrees Celsius. Okay, you already have the C, which is what? Negative 8. So let's substitute that to the equation. So we have T is 14 is equal to 18 plus negative 8 e to the k. So what is T? That is at 1 minute. Right? So let's simplify further. That's 14 minus 18 divided by 8 is equal to e to the k. So 1 minus k is k. Alright? Okay. So the right side of the equation, what is that? So that is negative 4 over 8. So that is 1/2 e to the, 1/2 is equal to e to the k. Okay, let's subject both sides to ln. So we have ln of 1/2 is equal to ln e to the k. This cancels out, and so k is ln of 1/2. Alright, so now we already have your k. Now, what was the last condition? So at the last condition, so it says here, how long does it take? So the time is not given. The temperature at this time is what? 16 degrees Celsius. And the temperature of your medium is still 18. Okay? We already have the C, which is negative 8. And K, which is what? ln of 1/2. Okay, let's substitute. We have 16 is equal to 18. So let's already put the negative sign, negative 8 e to the ln of 1/2 times time. Simplify. That's 16 minus 18 over negative 8 is equal to e. So T ln 1/2 is also basically ln 1/2 to the t. Simplifying. So we have what? (16 minus 18). That is negative 2 over negative 8. Then e to the ln cancels out, that we are left with 1/2 to the t. So this is basically 1/4, 1/2 to the t. And so we do ln on both sides. So basically, what happens is that we have ln 1/4 is equal to t ln 1/2. So we have t is equal to ln of 1/4 over ln of 1/2. So if you calculate that in the calculator, your t is at 2 minutes. That is then the solution. All right, let's have another example. Okay, we have a metal that is heated up to a temperature of 500 degrees Celsius. It is then exposed to a temperature of 38 degrees Celsius. After 2 minutes, the temperature of the metal becomes 190 degrees Celsius. When will the temperature be 100 degrees Celsius? And what is the temperature after 4 minutes? All right, let's rewrite the equation first so that we will not forget. Okay. Now, what is the given, or what is the first condition? So at time 0, what is temperature of the metal? That is 500 degrees Celsius. And what is the temperature of the medium? It is 38 degrees Celsius. Now let's substitute that. So we have 500 is equal to 38 plus c e to the k at time 0. So this is basically 1. And so you have 500 minus 38 is equal to c. And so c is 462. Now, next condition. So at time 2 minutes, what is the temperature? You have 190 degrees Celsius, and the temperature of the environment, or the medium, is still 38. We also have the C, which is 462. So let's substitute to the equation. So we have T at 190 is equal to 38 plus, what is C? We have 462. E to the, what is K? We don't have the K yet. And the T at 2. All right. So let's simplify. 190 minus 38 over 462 is equal to e to the 2k. All right. So what is 19? This, the right side of the equation. So that is basically 152 over 462 is equal to e to the 2k. So let's subject both sides to ln. So we have ln of 152 over 462 is equal to ln of e to the 2k. So this cancels out. We are left with 2k times ln of 152 over 462. And so we have a k of ln 152 over 462 divided by 2. Now we already have the K. So what is the other conditions? So we have one condition without the time. So we have at unknown time. What is the time at 100 degrees Celsius of the metal? Also, the temperature of the environment is still 38. We have the C, which is 462. And we have the K at what? ln of 152 over 462 divided by 2. Okay, let's simplify this. So if you simplify this, K is basically negative 0.5558. So that's for easier calculations. So K is basically negative 0.5558. All right, so let's substitute to the equation. 100 is equal to 38 plus 462 e to the negative 0.5558 t. All right. So what happens next? So we simplify. So we have 100 minus 38 over 462 is equal to e to the negative 0.5558 t. We'll subject both sides to ln. So you have ln of 62 over 462 is equal to ln of e to the negative 0.5558 t. This cancels out, so we're left with ln of 62 over 462 is equal to negative 0.5558 t. So if you manipulate the equation and find t, you will get t at 3.61 minutes. Okay, how about the other condition? So what is the temperature at 4 minutes? So we are given with the time at 4 minutes. What is the temperature of the metal? And we also have the surrounding temperature of still 38 degrees Celsius. And we already have the C and K. So C is what? 462. And K is at negative 0.5558. So substituting, you have the T. You have the T is equal to 38 plus 462 e to the negative 0.5558 times 4. So pretty straightforward. You already have the temperature. So if you calculate that, the temperature is at 88.0171 degrees Celsius. All right, so that is one application of the first order differential equation.